So, a very warm welcome to you all to this session, which is a hands-on experience session. We'll be giving you practical training on molecular docking and molecular dynamic simulation. First of all, we'll go through some slides to know the basics. So, computer-aided drug design is a technique for the investigation of molecular structures and properties using computational chemistry and biology and graphical visualization techniques in order to provide a possible 3D representation. So, docking explores the interactions between the atoms, between the molecule when a ligand attaches itself to the docking site of another molecule, usually which is a large protein known as a receptor. It involves computational filtering of a large body of molecules, and it identifies those binders that have a high probability of activity in the biological test system. So ligands may be of different type. Here different colors and shapes show different functionalities and different symmetry patterns of the molecules binding to the protein. This gap shows you the active site. So the significance of docking is to investigate and find the lead or hit molecule on the basis of binding free energy, that is delta G binding. So binding free energy is collection of all the following thermodynamic energies: hydrogen bond, electrostatic energy, torsional free energy, dispersion and repulsion energies, what we call van der Waals forces, desolvation, total internal energy, and unbound systems energy. The unit of the docking score is kilocalorie per mole. It's commonly used for virtual screening, can also be used to test possible hypotheses before conducting costly laboratory experiments. Docking programs predict how a drug candidate binds to a protein target. So, to perform molecular docking, you should have a protein structure that you can download from protein databases such as RCSB protein data bank, PDB-E, which is from Europe, PDB-J from Japan, BMRB, which is Biological Magnetic Resonance Data Bank. To find out the ligands, you have chemical databases like Zinc database, PubChem, Drug Bank, ChemBank, eMolecules, and Campbell. From here, you can download different chemical molecules to act as ligands. As in the today's lecture, it was taught to you about molecular docking and molecular dynamic simulation. The speakers have already given you an insight into this. Next is what are docking softwares. So Autodock, which is freely available, Gold, Discovery Studio, Glide. Autodock is the most common software because it is freely available and comparatively easy to understand as it has graphical user interface. So today we'll be telling you how to perform molecular docking using Autodock. What are files needed for Autodock winner? PDB file of target protein, PDB file of ligand molecule, text file of protein grid coordinates. Mole file of the ligand has to be changed to PDB format. This can be done with the help of molecular file converter, which is online, or with the help of Open Babel converter, which is offline. Now how to prepare the protein? Open the target file in Autodock. File, read molecule, open target file. Edit hydrogens. Edit charges. Add Coleman charges. Edit charges. Check totals on residue. Spread the charge. Edit atom. Assign AD4 type. Then you save the file and write PDBQT. Then copy all the residues from left side and add them on right side. Then browse your folder and save the file as target.pdbqt. Then press OK. Now you prepare the ligand file. Ligand input, open PDB file of ligand. OK. Ligand torsion tree, detect root. Ligand torsion tree, show root marker. Ligand torsion free, choose torsions, done. Then ligand torsion tree, set number of torsions, dismiss. Ligand output, save pdbqt, save as ligand.pdbqt. Then you have to do the grid box preparation. Grid macromolecule, choose target, select the molecule, save as same name with pdbqt extension. Grid box, give the coordinates if you know, otherwise keep as default and close it. What is molecular dynamics? It is a numerical method for studying many particle systems such as molecules, clusters, and even macroscopic systems such as gases, liquids, and solids. It is used extensively in materials science, chemical physics, and biophysics, biochemistry streams. Force field is used to calculate forces on each atom of the simulated system. It follows Newton's mechanics, calculates accelerations, velocities, and new coordinates from the forces. As we all know, force is equal to mass times acceleration. F is equal to ma. We have all studied. The atoms are moved slightly with respect to a given time step. So molecular dynamics is all about that you are simulating the molecule in terms of time, and you have divided the time into discrete time steps. Here we consider 1 femtosecond to be a time step. So your whole simulation is divided into discrete time steps. Molecular dynamics means you have different atoms bonded through different kind of bonds, and there are different type of motions or transitions taking on inside the molecule whose speed has been limited in terms of time, that is delta t is 1 femtosecond, and we are having rotation of buried side chains, local denaturations, allosteric transitions, hinge bending, rotation of surface side chains, elastic vibrations, bond stretching, and so all these are taking up. So what happens? Rotation of buried side chains, local denaturations, allosteric transitions take place in the seconds time, and hinge bending and rotation of surface side chains, and they take place in terms of time nanoseconds, and in bond stretching etc. takes in picoseconds, but molecular dynamics time step is 1 femtosecond. So now what you do is you calculate forces between the atoms, the different atoms of a molecule that are taking place. So what happens in a molecular dynamics simulation, that you are giving movement or trying to observe all the motions in a molecule within a certain time frame. So you have different energies at different temperatures for a molecule. They may be kinetic, coulombic, van der Waals, bond energy. So all are differing, and this potential energy is a sum total of all these kinds of energies. So in molecular dynamics, the steps include initialize position and velocities, then you equilibrate the system, then you control the simulation. Thereafter, how do you initialize positions and velocities? Positions are usually defined on lattice or at random. If knowledge about the structure exists, use it. Velocities are assigned random values. Magnitudes reflect desired total energy or in terms of temperature. Average velocity should be 0. So this initial state is not the equilibrium state. It will take the system means the entire molecular system, the entire complex's molecular system, some time to reach equilibrium. So equilibration after initial setup or after change of parameters, system is out of equilibrium. That is, its properties will not be stationary but drift, relax towards new equilibrium state. If we are interested in equilibrium, we must wait for a number of time steps to reach equilibrium before measuring observables. So what happens is, initial coordinates have bad context. They cause high energies and forces. Minimization finds a nearby local minimum. Then with the change of temperature, you either do heating or cooling or equilibration at fixed temperature permits the biopolymer to escape local minima. Then with increase in time, the temperature falls and the system becomes stabilized. So longer dynamics accesses other intermediate states. If you do molecular dynamics simulation for a longer period of time, you achieve different intermediate states and then you can have the most stable state. So here what you can find out is the number of transition states that it undergoes. So equilibration estimates each particle should have had a few collisions that are necessary to exchange energy. Particles should have moved at least a few typical interparticle distances. So when the collisions are happening, the particles have gained some energy and they should have moved to some distance, means there should be some change in the bond length. Watch a characteristic observable and monitor its approach to a constant value. If energy, n number of particles and v the volume are fixed external parameters, you have to watch T or P, that is temperature or pressure, and then compare runs with different initial conditions. Now how do you control the system? Thermodynamics system has a number of state variables which describe its macroscopic state like particle number, volume, temperature, pressure and total energy. They are not all independent but connected by equations of state. Example, ideal gas of non-interacting point particles. So now what happens is you have a canonical ensemble, number of particles, volume and temperature, what we call NVT. So they are static parameters. Now your observable values are total energy and pressure. So it requires a thermostat. To maintain a constant temperature, you require a thermostat, an algorithm that adds and removes energy to keep the temperature constant. Most frequently used are Brentson thermostat and Anderson thermostat. When your canonical ensemble is NPT, means your static parameters are particle number, pressure and temperature, then your observable values become total energy E and volume V. So to perform such an experiment, you require a barostat in addition to the thermostat, an algorithm that changes volume to keep the pressure constant. So this is how, when you run a molecular dynamics simulation, your outputs are a graph generated in the form of root mean square deviation versus time in nano or picoseconds. So how to analyze this? This would be energy. These are Leonard-Jones interaction energy, and this kind of graph you will get. So what are the advantages of molecular dynamics? It gives complete knowledge of system. If all trajectories are known, everything can be calculated. It easily accommodates non-equilibrium states and other complex situations beyond thermal equilibrium. Its applications are: the most basic and intuitive application of simulation is to assess the mobility or flexibility of various regions of a biomolecule, to investigate a biomolecule, large protein molecules, where their active site exists. You can find out from active site finder. Thereafter, you can find out which part of that protein can be fluctuated, is mobile, can be twisted, the conformations change in which part of it. All these studies you can do by doing molecular dynamic simulation. An important application of MD simulation is to determine how a biomolecular system will respond to some perturbation. Means how it will behave when any of the parameters like temperature, volume, or pressure will change. Applications are: you can remove a bound ligand from an experimentally determined protein structure and then simulate to see how the ligand's removal affects protein conformation. You can replace a bound ligand by a different ligand and see how it affects protein conformation. You can mutate one or other amino acid residues in the protein, for example, to explain or predict the functional effect of a mutation, or to recover the wild type structure in cases where the experimentally resolved construct differed from the wild type. So you can plan different kind of experiments with the help of molecular dynamic simulation. You can phosphorylate an amino acid or add some other post-translational modification. You can change the proteination state of an acidic or basic amino acid. You can apply external forces to simulated atoms to capture the effect of transmembrane voltage or of mechanical strain. You can change the molecular environment of a simulated protein, such as the salt concentration or the composition of lipids in a membrane. So now we will start with the practical aspect of it, which my group members will be telling you. So I request you to listen to them carefully and learn this step by step. So now I would like to hand over the session to my group members, Akhilesh and Vishwajit.
Thank you, ma'am. Is my screen is visible? Now, we will go for the demonstration of Autodock winner for the docking of the ligands and proteins. First of all, we need a molecule and ligand molecule for the docking. Then we have several database of the proteins, as ma'am told that PDB one of the most commonly used database for the protein. Search here a protein molecule. If suppose we I want to dock a protein of diabetic proteins with two side each. There are so many uh, PDB ID for a single protein. We have to choose that one which have a highest enrichment energy and lowest resolution. We can choose any one for the demonstration. We have to choose this one. Download it in PDB format. Save it in your required in a working folder. Now we have to download a ligand molecule. You can log a single ligand with a protein and multiple ligand with a single protein. Uh, uh, Chemistry database is a PubChem. From here we can download any one ligand which are available in this database, such you can take this one. We have to download in 3D form. Here we have to download in the 3D conformation in the format of SD. Now we need to change the SDF uh, SDF ligand in the mole or PDB format because Autodock accept only mole format and PDB format. Then we have to change this SDF format to the mole format. Mm. You can use PyMole, use PyMole. This is our we can see the protein, delete a water molecule, ligands, and other molecules in this here by selecting the non-proteinous molecule. Now we have to have to open Autodock. नहीं देना अब दे रहा है ओके delete everything. This is the protein molecule with the water ligands and other elements. Now we have to remove all the waters and other non-proteinous molecules. Then we can select here and remove it. This is the non-proteinous molecules from here to here. Non-proteinous molecules. PDB. नहीं दे रहा क्या? Sub it in PDB format. Okay. Then we have to open a Autodock on your prepare the protein. We can export the protein file, read molecule. Hello. Okay, this is our protein. So first of all, we have to prepare it. Go to the edit and delete water molecule, which we have already deleted in the py mode. Now we have to add a hydrogen on polar only, then click OK. All polar hydrogens has been added. Then we have to go charge and add Coleman charges. Click OK. Then we have to go charge and check total residues and dismiss. Then go to charge. And go to the atoms and assign AD4 type. Now we have to save this protein file in the format of PDBQT. Write PDBQT. No. Select R1 add. Okay. Then
उसमें सही सही ईमेल आईडी भी नहीं दी है।
क्या
उसने ईमेल लिखा है तो ढेर बड़ा कलाकार पेपर में तो बोल रही है देखो नहीं चाहते वो दोनों लोग एक जगह से हो जाएंगे।
say between the CDP QP format. PDB-QT format. Now we have to input. Here R file. This is our ligand. Now we have to go torsion tree, root, then go again torsion to detect root, then go to the torsion at the PDBPT. Okay. See all these files. This is our protein. Now we have taken. Hello. We have two proteins. In weight molecule, PDBQT, open it. This is the protein. We have to prepare grid. On the grid box. This is the box. Grid box. We can set which size from here. And we can set a grid from where our ligand binds. We can adjust the box regarding to our need from where we want to dock our protein or a specific ligand, a specific amino acid. We can choose it from the other method. We can increase the box size from here. Now we have to make a text file uh, in which we save the dimension of the grid box like this one. This is the X, Y, and Z dimensions, and this is the center grid box. We have to write it in the text file. Here, this is the 29 point. Have to write dimension size 62. For here we will write the protein, which is the name of the file. the ligand file name, that is a this one, and open the power window. And go search the path of the Autodock where we have installed. We have to copy it, then we add the path here. This is the path. See, this is the part of Bina, and other one is the command for the doc configuration. Vina text out. This is the result of the docking. Most if result is a minus 7.9, then we are going to the lower energy, lower binding energy. So best one is the minus 7.9. This is the best of position in the protein of the ligand. Now we have to learn the how of multiple ligands in the single protein. We have to make a folder of the ligand. The ligands, single file. I think there is some technical error. We are handovering the name presentation to the Visujit. 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 Visujit.
Yeah, I can hear you.
Start your session. ये फोन भी नहीं काम कर रहा है सुनाई.
Good afternoon, everyone. I hope my screen is visible to. So basically, in docking session, we have seen about the protein preparation and ligand preparation, and then docking the ligand with the protein. And the protein and ligand files were converted into PDB Qt format, because Qt format will basically have the atom type and the charge embedded in them, unlike the just PDB format. So I'll just show you a visualization of the same thing, like over here. VMD is basically a free tool for molecular and to visualize the molecular dynamics simulation results. The protein is a protein that we are. So as you can see, this is a protein, and then we will load the ligand molecule, which is over here. If you would like to have a more better understanding of this thing, you can load the complex file, which has the merged protein and ligand molecules. You can see the graphics presentation. Color so that it should be easily visible. This blue part is the protein and all, and then we create a representation for the name of the ligand is UNL over here. Basically, this red part is the ligand which has been docked onto the protein. So basically, in docking, the protein is considered to be rigid in nature, and in molecular dynamics simulation, we will be analyzing or understanding the flexibility of the protein and the stability of the ligand at the active site. And as Dr. Rituraj Purohit sir has actually explained in very detail regarding the molecular dynamic steps, and as well as the commands from the Gromacs simulations, we'll be seeing the same commands over here. And these are basically the commands explained by the Purohit sir. So first of all, after docking, we will be having a protein structure and a docked ligand structure. And most of the force fields does not directly have the parameterization capability of the ligand molecules. So we'll be needing a third party tool to create the parameters of the topology of the ligands. So few of them are like this one, ProDrag is one of them, and then we do have the CGNF is another server, and then we have the Swiss param over here. Yeah, so Swiss param is another tool which can be used like. So these three different tools that can be used to parameterize the or generate topology of the ligand. So in this one, we have used in this tutorial we have used the ProDrag to create a parameter file of the ligand. So the topology file of the protein has been generated, and the topology file of the ligand has been generated using ProDrag. So now we need to go for the simulation part. Like first we need to prepare the system. To prepare the system, we need to confine the protein and ligand in a box. So these are basically the steps explained by in previous session. So complex GRO is a complete complex file of the protein plus ligand. The output will be a new box, which will which means that the protein and ligand will be confined in the box, and the box type is a dodecahedron with a distance of 1 nanometer from the edges. Now we have a once we run the command, we'll have a box with the diameter, center, and everything is given over here along with the vectors and all. So once we have a new box, we need to solve the complete system. Solid in the sense we need to add the water molecule, because generally in our body, like the protein will not be in vacuum, right? It will be in a saline region. So the next step will be to solve the system. Yeah. Now I can show you the solvent. Yeah. This was basically just a protein and ligand, right? Now as you can see over here, it's the protein is completely confined in a water box. But a molecule also has because it will not be in a excited state, right? The system should be neutralized. So in our body, we'll be having saline salinities like sodium and chlorine ions. So we'll be neutralizing the system using the sodium and chlorine ions as required. So first we need to create a parameter for that. Over here we are specifying the parameter file. You can see over here the parameter. All the conditions that we would require for the simulation should be specified in the parameter files. Over here. The algorithm, the number of steps and everything. Yeah, the next step is we need to prepare the system for to add the ions. Oh, sorry, I haven't done this step. We will be adding the you select the solvent molecule, continuous group of solvent molecule, which is the solvent over here. Because water and solvent are identical over here, but in some systems, we could be using ethanol or something else as a solvent. So we could select the solvent over here. So as you can see over here, like around 12 sodium ions are added to neutralize the system. And once we have neutralized the system, we will be going for energy minimization. So again, we have a parameter file of energy minimization over here, where we'll be specifying the algorithms and the number of steps that we need the cutoff schemes and everything. So we need to prepare the energy minimization parameter file first of all. Yeah. So now we'll go for energy minimization run. And further, exactly the same thing, like we can go for NVT ensemble for uh, stabilizing the or ensembling the system for constant volume and pressure, and then finally run the production run for as many steps as much as needed. But because as it has been stated that molecular dynamic simulations would need a specific type of systems, and I am running on a personal laptop, it would take an extremely long time to run this thing. So I'll just show you the output of the results from here. Because if I just let it run, it might run for a few days or even few hours. So the same simulation I have already performed earlier on the high performance computing facility using the exactly same steps, which I'll be showing you. So this step, and we'll be loading the trajectory file into the molecule. Stride is like you specify what all frames to load. If you specify to load everything, all the frames, it could take a lot of time and memory and all. To be done on a high-end high spec station laptop. You can just load every 10th frame over here. So it's loading. And further, we can go for the analysis over here. First of all, I just clear the water from the thing. The protein, and I'll create a representation for ligand. I just change the name for ligand for better visualization. The color and all. Yeah, if you can see over here, the red one is the ligand and the blue one is the protein over here. We can run the trajectory once again to see how. So you can see over here, the ligand is very like interacting with the protein and is not uh, getting released from the protein, which could specify that the ligand and protein binding is quite stable in this case. So further to visualize the RMSD and the timeline analysis, we can use the VMD itself to analyze it. And go to extension analyze and analyze RMSD visualization tool, which will specify the clear everything.
Hello. Yeah.
Protein.
Jay?
RMSD.
Catching dead. ये तो होगा तभी तो क्या बातें कर उनको बोल दिया अवनीश सर को तो उसको जल्दी चाहिए उसका करने के लिए वो कह रहे हैं एक महीना अवनीश सर को बोल दिया और रात में 3 दिन लगा देंगे एक तो आज लगाएंगे एक कल मेरे सामने लगाएंगे फिर आज उनकी शाम को लैब है तो शाम को टाइम नहीं मिल पाया तो कल एक में आज लगा
protein RMSD, and then we can expect the residue of the ligand. Oh, sorry, the ligand is 2NL over here. Don't have that information. So the protein and ligand will plot the results, and over here you can see the RMSD of the protein in blue and the RMSD of the ligand in red. How the conformation is changing during the whole simulation time. It's a RMSD versus time plot. The frame over here, RMSD in angstroms, and the frames over here, like we have 100 frames over here. And for further analysis about regarding the same, we can go for various tools like timeline analysis, where we can calculate the secondary structure of the it will take a while. As you can see, the second structure is getting generated. So there's a change of the secondary structure over the whole simulation time. We had 101 frames, and each color represent a specific secondary structure over here. And if you'd like to visualize the changes in the secondary structure in the electric protein, we can select the specified location over here. Like suppose like there's a minor change over here, like, and we select the part. The same thing will be highlighted over here, the red one. Like I'll just for a better visualization, I'll just remove the ligand and change the protein to different. Yeah. So this red part will specify the location of the this residue from over here. Like likewise, we can select different locations from here, and it automatically gets updated in the over here. And again, we have various types of analysis even where we can calculate the RMSD, RMSF, the second structure which we have seen, the pi values, the hydrogen bonds, and intermolecular contacts and all, which can be explored further. And like as we have like seen that, as we have already heard that, molecular dynamics requires a specific type of computation system, like high performance computing for faster performance and everything. But when the faculty are teaching the students, like not all the students could have the access to the high performance computing facility and all. So there's one more online like lab tool known as Galaxy, which is a computation. It's basically a collection of workflows related to bioinformatics and computational biology. So even in this thing, we have like Galaxy is a free tool, like anyone can register in this thing and run. So we do have like Gromacs even in this thing, which can be used for the simulation work. So I'll just show you the basic steps even over here from the starting. So firstly, we would be requiring a PDB file. Like in this thing, I'll be showing how to simulate a protein molecule. So we'll be needing some PDB file. We'll take the small file over here. This is the lysosome, which has around like 129 amino acids. So we'll consider this thing over here. 1 AKI. The different modules over here. Like this module will help us to like upload, like to download the PDB file. Like there are the modules to upload the PDB file of our own. Like this thing I used downloading this one from the PDB. So the PDB file has been downloaded. So here in the PDB format, if you like, and now you can see over here. With a complete PDB file, and this even has the heteroatoms over here, like basically the water molecules over here, which we do not require for simulation work, because we'll be adding the water molecules after topology generation. So we need to remove the water molecules from this PDB file. So for that thing, we can use the text editor. First, next place, like, so we'll match all the yeah, we'll remove everything which does. First one is the second one. Don't match the heteroatoms. The heteroatom that we have seen earlier. And case insensitive and execute. Now, as we can see in this thing, like if you can visualize the file, all the heteroatoms over here are removed in this thing. Like we only have the atoms part in this thing. So now we can go for the initialization step of the Gromacs. So there's a module known as Gromacs initialization setup over here. The water model we can specify as required. We'll specify in the table 3 over here, and the input will be the this thing, like the PDB which has the heteroatom removed, and we can specify the force fields over here. It contains like OPLS, Gromacs, Amber, Charm, and everything. Like we'll just specify OPLS over here. Like everything will work over here. Like, and there are different parameters which we can specify over here, like ignore hydrogens, generate detail log, and everything. Then we can even have a email notification. I'll just execute it. And once the initialization step is done, we'll be going for like box preparation, just like how we have done offline. That's now. We'll be going for structure configuration, where we will be adding the box configuration box to yes. Okay. The input file will be the latest one, and box dimension will be again one. The larger the box size, the bigger the system, and the larger time it will take for simulation. So one would be the ideal one. Not ideal, but it would be a very all sides should be equal. Like you can specify the shape of the box over here. Like, and again we can specify the detail log or email notification over here. So now that we have the box completed, we'll be going for solvation. We have a module known as Gromacs solvation and adding ions. You can see over here. The input will be again the latest grow file. The topology will be it will be automatically selected unless we want to change it. The water molecule can be selected again depending on our requirement, and we do need to add the ions to neutralize the system. The concentration can be specified if required. The solvation is done. Now we can go for energy minimization. There's again a module for the thing, Gromacs energy minimization. Again, it will be automatically. And this thing is the parameter file that I have like shown over here. Same thing over here. Like either we can upload our own parameter file, or we can use a default parameter setting which can be configured online. So it will be completely similar to the one that you have seen over here. So here, the integrator, like the algorithm that we need to use, the electrostatics, the nearest neighbor, all these things can be specified, and the major part that needs to be specified is the number of steps for into simulation for like Python over here, and the energy minimization toleration over here. So how long should the energy minimization run? Like what should be the maximum force on each atom? So you can specify that 10 kilocalories per mole. Again, the time step and all. The smaller the time step, the more accurate it could be, but the longer the simulation would last. Again, specify the log and email. It will take a minute to. Once energy minimization is done, we'll be going for simulation, in which first of all we'll be going for conserved ensembles such as like NPT, where we'll be stabilizing the system at constant pressure and like volume, at constant temperature, volume, and pressure, so that we will be not having any further complications during simulation. Yeah, basically it's taking a while. Much simulation part over here. Once the data is generated over here, we can go for like input over here and the Gromacs topology input and the checkpoint if we have them. And if you like to restrain some molecule, or so maybe restrain the ligand to prevent it from showing too much deviation, we can restrain them and then index file and all the default parameters and everything. And now over here you can specify the structural output and specify over here. Settings. In settings, we'll be having we can select the NVT, NPT, or directly like the MD1. That's how we can do the ensembling. Basically, very identical to the ones we have done over here. Like we have done the box, confining it in the box, then solvation, neutralization, and then we have energy minimized. And further, we can go for NVT, that is conserved ensembles, NVT conserved ensemble, and then go for the molecular dynamics simulation. Because it would take a very long time for this thing, it could not be shown in this today, but the end results have been shown here. Already so this basically I can see few charts over here. Okay, I'm sorry for the errors, disturbances in the audio. Can we run Gromacs in our system, or do we need to specify? Oh, we can actually run Gromacs in almost any Linux system, but on a normal system, it would take a very long time to run the simulation. So it is not advisable to run on a normal system. And yeah, open source is a Linux environment. Basically, I'm using a Linux subsystem upon my Windows system. It's basically a Linux subsystem running on the Windows. Gromacs can run on Windows also, like using few emulations like Cygwin and Megwin, but that would be very slow. I will not recommend running on Windows, because anyway, like even if you run on the Windows, the backend would be Linux only. So that's the tutorial. Like um, so if you have any other queries, like I can answer, or Nidhi Mishra ma'am can answer.
Okay, so participants, do you have any questions to ask? Any queries? So Vishjit, Wasim Ahmad Ansari asks, how can complex file compile in GPU?
No, complex file compilation does not need require any like specified system and all. Like it's basically a complex file is just a, so you can see over here, like, it's basically a text file. Like you can just, I just share my screen once again. Complex.gro is basically a text file containing the protein and the ligand. You can see over here, these all are protein molecules, residues and all. And over here you can see the ligand residues. Combination of protein and ligand will create a complex file, and we do not require a specified system to compile them. You can do it on any like text editing tool. Yeah, Autodock is basically a free tool, and as you can see over here, like Autodock is basically a free tool, like, and XYZ Center in Autodock is actually specified if we know the docking site. Suppose like if we do not know the active site of a protein, we could confine the whole protein in the grid box, or we can go for other tools which are like active site prediction tools. That will be RESTful tools for that. And if we know the active site, we can specify the specified XYZ centers in Autodock.
There is a request from Vivek Sonavane to demonstrate Swiss param. We will take it tomorrow because today it's almost 4 o'clock, and tomorrow we will definitely like to take your problem that to demonstrate how to use Swiss param. Is there any question related to molecular dynamics simulation? You can ask now. So I just hope that there are no more questions to be asked, and we should end with this session. I thank Akhilesh and Vishjit for demonstrating you molecular docking and molecular dynamics simulation. So you can ask us any question related to demonstration. The email IDs of both these guys were provided to you on the leaflet. So you can drop a mail if you have any doubt. And we have uploaded all the videos till yesterday, till afternoon. So you'll get a link for that. Okay, so I think everything is quite clear to us till now. Tomorrow definitely we will take Swiss param and homology modeling in the hands-on experience session, and we will have lectures in the morning session. Okay, so I thank you all.